I mean, yeah,
Okay,
the title page.
Okay, so welcome to our first seminar between Professor Monien's group at University of Bonn and our group in Paris on statistical physics. And our first on our talk today will be on fast sequential Markov chains by Philipp Höllmer, and its work that he has done together with Liang Qin. Also here present, you are coming in from Beijing, right? Liang?
Me?
No, Liang Qin.
Oh, okay.
So you are now in Beijing? Okay, we don't hear him. Okay, all right. So anyway, so please go ahead, Philipp.
Okay, thank you for the introduction. In the next 45 minutes or so, I'm happy to present the fast sequential Markov chains or our work in it. And as Werner already said, I didn't do the work alone. I did it in collaboration with Liang Qin and Werner Kraut. And you can find 2 versions already on arXiv. And if you're interested, you can have a look at this arXiv paper here. Before I start with the description of our fast sequential Markov chains, I would like to motivate our work a bit so you all understand why we studied this in the first place. So as you all know, I am working together with Liang Qin, Tony Max, and Werner Kraut, who are all here today. And we are working hard on developing the jellyfish application, which implements the Markov-chain Monte Carlo algorithm for a wide range of all atom systems in a very general way. And right now, it can treat interacting atoms, dipoles, and water molecules, and it is eventually aimed at to simulate peptides and polymers, so to do molecular simulations. In May, I gave already an online seminar with an extensive introduction into the version 1.1 of Jellyfish. And this online seminar is available on YouTube, so if you're interested, you can check this talk out at the given link. Why I'm showing this here, you can see in this red box, because back then I was able to state that Jellyfish version 1.1 allows to simulate up to 10,000 water molecules with the Salveto algorithm. And for this, we use the SBC-FW model. So we were very happy that we can do these simulations using Markov-chain Monte Carlo algorithm. And so what we did is try to run some benchmarks. And as a benchmark, we used the decay of the autocorrelation of the dipole moment P of a water system, because this dipole moment is usually the slowest mode. And for your information, the dipole moment is coupled to the rotations of the water molecules. This plot here shows basically plots of autocorrelation. So on the y-axis, we plotted the normalized autocorrelation, and on the x-axis, we plotted the per molecule displacement in the Markov-chain algorithm. And all of the curves in this plot use different numbers of water molecules, but we all put them in the box of the same size. So and this box has the size so that at the highest number of molecules, 212, we have the aim density, so to say, at which we want to simulate water in the end. So between each curve, the density increases. What you can see in this plot is a problem, because you see as we increase the density or the number of molecules, that there are 2 timescales appear. So it's not exponential anymore as for one water molecule, but we have a very fast initial decay here in this small region, but then it kind of goes off on a very long decorrelation time. And this gets more severe as we increase the number of water molecules. And this effect, these 2 timescales, lead overall to only a very slow decorrelation of the dipole moment already in this very small system. Of course, we weren't very happy with that, and we tried a lot of things, like, for example, doing solid motions of the full water molecules, or we tried a lot of different parameters. But in the end, we unfortunately had to conclude that our naive version of Markov-chain Monte Carlo, where the velocities of each event chain are parallel to the Cartesian axis, only rotates dipoles slowly. So we describe the water molecule as a dipole here. This is depicted by this movie on the right, where you can see for a 2-dimensional dipole, for example, and you see that each event chain first goes in X direction, and then we go in Y direction, and then in X direction again. And this, as I said, leads to very slow rotation of the dipole, although we can in principle rotate. Additionally, direct rotations of our dipoles are not feasible, so we have to think about something else. To kind of solve this, so this concludes the motivation of our work, we want to rotate dipoles faster, or molecules in general. For a solution, we went back in the history of Markov chains to the first description of the Metropolis algorithm by Metropolis et al. In the year of 1953. They did it in their well-known paper. I am sure all of you had a look at it once. And there they describe for a particle system how you can construct a Markov chain that samples the Boltzmann distribution, basically. Their procedure, it was basically composed of 2 steps. So step 1 is described in the left paragraph. Here you pick out a single particle and you propose a local move by displacing this atom to another position in its neighborhood. And the step 2, which is described in the right paragraph, there you accept or reject the local move based on the energy change due to this configuration change. Why I'm showing you this here is due to this sentence, which I highlighted with the red box. There's a very interesting part in the description on how they propose a local move. Instead of picking a particle at random, which should move in the next single atom move, they move each particle in succession. So what they do here is they do a sweep of particle indices. Unfortunately, they don't explain in this paper at least why they use this, but the reason is probably, and it turned out later to be true, that this particle indices sweep is somewhat more efficient than picking a random particle. This sweep of indices is also very usual in spin systems. So there you don't sweep over the particles, but over the spin indices. On this slide, I show you the reason for doing spin sweeps at the example of the 3-dimensional Ising model at 14 cube lattice sites, and I took the table from the Berg book. This table compares integrated autocorrelation times of a simple reversible Markov chain simulations at different values of the inverse temperature. And we either do a random choice of a spin, which is tried to flip in the next move, or we do a sequential choice. So this T in random is the random choice, and T in sequential is the sequential choice. So let's go through some entries. So at beta equals 0, which corresponds to infinite temperature, of course. If you use the Metropolis algorithm for the Ising model at infinite temperature, you definitely flip the spin when you propose a move for it. So what you do here, or what you can see here, is we measure the integrated autocorrelation time in time units of a sweep. And you see that, as expected, the integrated autocorrelation time of the sequential scheme is just 1, because we just go through all spins and we flip every spin. However, for the random scheme, it's a bit higher because we don't necessarily flip every spin during one sweep. For lower temperatures, you can see something very interesting happen. So if you compare all the integrated autocorrelation times between the different schemes, you see that the sequential spin sweeps always lead to a somewhat more efficient simulation. So to conclude my introduction on sweep methods, sequential sweeps of particle or spin indices can be somewhat more efficient. This is known for a long time, and this is why they're usually used. I want to mention that strictly speaking, these sweep methods are non-reversible. This is easy to see because the reverse move, where we update the particles or spins sequentially in the reverse order, never occurs. But still, although this is strictly speaking non-reversible, one can see that the probability distribution is still explored by means of a diffuser's random walk. At least as long simple Markov-chain methods as Metropolis and heat bath algorithm or the Gibbs sampler are used. Of course, you can always think about hybrid Monte Carlo, so there where you try to suppress this diffusive random walk. But as I said, here we do a diffusive random walk still. So now we stopped at this and we thought, okay, we do these sequential sweeps of particle or spin indices, but they still do a diffusive random walk, which is a bit faster. But why should we stop there? And this led to our idea of fast sequential Markov chains. So instead of sweeping over particle or spin indices, we thought about sweeping the direction. So we modified the direction of a local move in any local Markov-chain Monte Carlo method deterministically. What I will show in the following is that this idea profoundly changes the trajectory of the random walk, so it's highly not diffusive anymore. Also, this idea can be more efficient than the random choice version, where I choose the direction randomly. And also, or in particular, we can obtain a divergent speedup compared to a naive sequential choice of the directions that are only parallel to the Cartesian axis. So this idea is therefore in particular useful for event-chain Monte Carlo simulations. However, I want to emphasize again, this idea can be applied to any local Markov-chain Monte Carlo method. So, as I said, our work is inspired by simulations of molecules, and our aim is to, in the end, rotate dipoles faster. If we look at the SBCFW water model, we see that it contains a bond interaction between two point-like atoms that depends only on the distance between these atoms. And the interaction kind of induces a harmonic fluctuation of the atoms around some given equilibrium separation. And this is actually also the interaction we used for dipole simulations in jellyfish. So what we first did to have a model we can study, we simplified this harmonic bond interaction by model to a flexible dipole which has a flat interaction. So we assume we have two atoms at two positions x1 and x2 at some distance rho. They only interact with this flat interaction, so we only allow distances which are in some interval between small r and big R. We use this simple method or the simple model instead of the more complex harmonic model, because then we get an analytically tractable testbed for molecules such as water. We now assume that we have some local MCMC method with local single atom moves, and we can always formulate this single atom move that moves some atom along a line L, which has the angle phi with respect to the x-axis. So in the following, I will always parameterize a direction of a single atom move by this angle phi. And these single atom moves then induce rotations or translations of the entire dipole. Our sequential MCMC Markov-chain Monte Carlo scheme then only concerns speedup of the rotation of the dipole just using single atom moves, and we therefore do not consider global rotations or translations of the full dipole. Of course, you can always mix it with that. So in this sketch, I show you the dipole and the single atom move. So here on the left, you can see the atom x1, the pink atom at some position, and another atom at position x2. And I depicted the allowed interval of the dipole separation by these gray squares. So this is small r and this is big R. We then have some local move, which moves the x2 position along this line L to a new position within the allowed region, of course. This single atom move along the line L can be anything. It can be done using the Metropolis algorithm, or it can be done using event-chain Monte Carlo. It doesn't matter for now. If you want, you can also view this dipole as part of a lot of dipoles, and then you just assume that you have hot sphere interactions between all of these spheres or atoms. But in order to get analytic results, we first studied a single dipole. Of course, if you only consider a single dipole, we can always factor out the position of the first atom, because any movement of the first atom x1 just induces an inverse movement of the atom x2. And this is why I will set x1 to 0, and then I define my x as x2 minus x1. And then I can describe this x in terms of polar coordinates. So I introduce the dipole length rho and the dipole angle. So then we mapped our dipole system onto an analogous ring system, so to say. So we have this pink atom now in the middle, and we have the blue atom out here. And this blue atom is only allowed to move in this ring here, which models our flexible dipole. And we are always interested in how fast we can change this theta angle. Of course, if you think about it, the very simple flat interaction just means that you have a flat probability density function within our ring omega. I also depicted in this ring system the same move as on the left sketch. So you have the line L again, and we move our atom along this line. In the following, we will notice that the so-called impact parameter lambda will become important. This is shown in this sketch here. So what is this impact parameter? The impact parameter basically depends on the direction of the local move. So it gives the signed distance in units of r of the line L to the origin. So I just do this line here. You can directly see if the absolute value of lambda is smaller than 1, then this line L has 2 intersections with the inner small circle. And then we have 2 segments S plus and S minus in which this position X can lie. In our discussion of sequential Monte Carlo, which will follow in the following, we introduce a so-called non-hopping condition. So we said that we only consider local moves which keep this blue atom in the same segment. So we don't allow jumps from here to here, which would in principle be possible in Metropolis, but very unlikely. Of course, if I increase the absolute value of lambda to values larger than 1, then I shift outwards this line, and then there is only a single segment, and there we don't need this non-hopping condition. So let's go now to the description of sequential Monte Carlo. Up to now, I always said that we can use any local Markov-chain Monte Carlo method for the local single move along the line L. In our paper, we studied basically a limit where all of these local Markov-chain Monte Carlo methods become similar. In this limit, we just repeat the local single atom move along the same direction until we reach restricted equilibrium among all accessible configurations that lie on the intersection of the ring with line L. So in this sketch, we start here, we do a lot of single atom moves, and then we just wait until we reach equilibrium on the segment S plus. In this limit, all local Markov-chain Monte Carlo methods like Metropolis, heat bath, or event-chain Monte Carlo are similar, and they all realize a direct sample among the accessible configurations. So in other words, instead of doing this infinite number of repeated moves, you can just sample the next position by drawing a uniform random new position on this segment S plus. And in this limit, we consider this limit, and in the following, I will always denote one time unit as one fixed direction phi t. And so we can now describe sequential Monte Carlo. For this, we
excuse me, just want to say, please ask questions, because if you don't understand it, you are in very good company, because our referee didn't understand this either. So, but maybe you're much faster in understanding than our referee, because if you go back one slide, just so that everybody understands what you are doing. Okay. All right.
So yeah, to emphasize again, we do not consider only a single atom move of, for example, event-chain Monte Carlo or Metropolis, but we do it an infinite number of times along the same direction, so that we always have a flat probability distribution on this line here, on this segment, on the loud segment. And this kind of unifies all local MCMC methods. And we do this, of course, because then with a very, very simple flat distribution, we can come very far analytically, and we can get very interesting results. Okay, and now we can basically, with this idea, we can basically write down our scheme for sequential Monte Carlo of a paper, and we do as always, using the lifting framework. So we kind of augment our physical space of the position xt by the direction phi t of the current local move. The sequential Monte Carlo scheme for a single time step then proceeds in 2 steps. So we first sample, as I already described, a new position xt plus 1 from a uniform distribution on the accessible configurations given the current position xt and the current direction phi t. And the step 2 is then basically the sequential sweep of the direction, because then afterwards we deterministically increase the phi t plus 1 to be phi t plus some change delta phi. So we don't choose a random new direction, but we always increase it by this delta phi. To kind of sketch this scheme, I made some plots for you. So here we have the ring system again. The pink atom is at the origin and is fixed, and we have the blue atom here, and it's at some position x0. And we assume that the first direction is at 0 degrees. So this means that the line L0 along which we propose a new move is just parallel to the x-axis. So now we do the first step. So we sample a new position along this line L0, and then so we just move our atom to the position x1. This was the first step. Now we have to rotate the direction. For this, we use the new position x1 as the center of rotation, and we just rotate L0 here by 20 degrees, so that we get a new line L1. And then we repeat basically. So now we have the new position x1 and we have the new line. We sample a new position on the line L1. So we get a new position x2, and then now we rotate again the line by 20 degrees. And we repeat. We sample a new position x3 on the line L2, and we rotate the line by 20 degrees. And this gets repeated indefinitely, and we will get very interesting trajectories out of that. So, of course, we now wrote down a scheme. What one always needs to do in Monte Carlo, when one studies Monte Carlo simulations, you have to prove that our scheme converges towards the stationary probability distribution pi. So we first prove that our algorithm satisfies global balance condition. So pi, as I already said, is the probability function that depends on the position and the direction. And we show basically that the flow into any position and direction is equal to its probability density. So here on the right, we sum over all other directions and positions, and then we have here this P, this transition probabilities. The global balance conditions is only one thing one needs to think about. The other thing is irreducibility. And of course, if we are in 2 dimensions, we can assure irreducibility for any choice of 2 or more directions. So, and with these 2 points, we can conclude that sequential Monte Carlo converges towards this desired stationary distribution pi. So in our ring system, that every position in this ring omega has the same probability density. I haven't written down the proof for the global balance condition here, but you can find it, of course, in our paper. But it's basically very simple, because this first step here, where I draw a new position with a uniform distribution, it is reversible, so the base detect balance. And the second step has a very simple deterministic form. And if you combine these 2 simple ingredients, you can easily show the global balance condition. So now that we have defined our scheme in which we can study the trajectories, we can look at some equilibrium properties. And as I already said, we are interested in the rotational dynamics. So we study the trajectory of the so-called rolled out dipole angle theta t. With rolled out, I mean that we don't wrap back this dipole angle into the interval from -pi to pi, but it can go over that. And we also study, because it will turn out that it's very closely related, the trajectory of the impact parameter lambda t. Just a reminder, the impact parameter was the signed distance in units of r of this line of the locus single atom move to the origin. And in the following, I will show you first the trajectory where we choose the new direction randomly in the allowed interval. And then I will show you, in contrast, the trajectory of our sequential scheme. So this is the trajectory of the random continuous choice of the new direction, and you can see nothing very interesting going on here. I mean, so on the y-axis, the blue curve shows the trajectory over t time steps of the dipole angle, of the rolled out dipole angle, and you can see it looks pretty much like a random walk, or like a diffusive random walk. And positive and negative rotations of our dipoles interchange very quickly. At the same time, the trajectory, which is shown in orange down here, of the impact parameter is fully random, because the impact parameter is strongly coupled to the choice of direction. So if I choose a random new direction, I also choose just a random impact parameter. However, this curve will change a lot if we now consider our sequential scheme. And I hope you're all surprised by this curve. because we can directly see that it's not diffusive anymore at all. I mean, first look at the trajectory of the dipole angle, for example. If you look at this part here, you can see that we have over around 4,000 time steps, a persistent negative rotation of our dipole, which proceeds in these interesting steps. So we have always some jump, and then it stays constant on a plateau, and then we have a jump again. Of course, there's a very small region that goes in the other direction, but we neglect this for now. We can see that this persistent negative rotation of a dipole is coupled to a very interesting trajectory in the impact parameter as well, because you can see here that as long as the dipole rotates in a negative sense, that the impact parameter performs these zigzags, and in these zigzags the absolute value of our impact parameter is always smaller than 1. Likewise, we do not only see these rotations in negative sense, we also see a very persistent rotations in positive sense. So here again, over what is this, 3,000 time steps. Here we do not rotate in steps, but we fluctuate around some average rotation, so to say. And while the dipole angle rotates in the positive sense, the impact parameter does something completely different. I mean, it does not do these zigzags anymore, but it does a very long excursion. And during this excursion, the absolute value of the impact parameter is always bigger than 1. So we see that there's something interesting seems to happen at the boundary of where the impact parameter has the absolute value of 1. And what we can conclude from this trajectory is, I mean, we are highly non-diffusive anymore, and that the trajectory of the dipole angle is very strongly coupled to the trajectory of the impact parameter. So what we do first is now we study the impact parameter a bit more closely. And we just consider now a single move, and we consider the change of this impact parameter lambda during a single time step. To understand how we can do this, go into the reference frame again where phi is 0, so the phi 0 reference frames. And so our line t is again parallel to the x-axis. This reference frame is good because then the lambda value is basically just the y value of our position. In our scheme, we now first choose a new position on this line LT and then rotate our direction to this line L by some delta phi. Based on where we sampled a new position on this line, this subsequent rotation will give a new value of the impact parameter lambda t plus 1. What do I mean with this? Assume that we sampled the very right edge on this line LT, so this is here, and then we rotate. Then you see that we get the smallest possible value of lambda t plus 1. So it's very close to the origin. Likewise, if we would have sampled the position on the left edge, we get the largest possible value of the position lambda t plus 1. And any position between the smallest value of lambda t plus 1 and the largest value of lambda t plus 1 corresponds uniquely to some position on this line here. Because this position has a flat distribution, of course, this lambda t plus 1 will also have a flat distribution. Because we now know the distribution basically of our lambda t plus 1 a random variable, we can write down simply the expectation and the variance. And here you can directly see why in this trajectory there was so distinct behavior for the regions where the absolute value is smaller than 1 or bigger than 1, because you can see that the expectation is has very different looking terms. So if the absolute value is bigger than 1, then it's proportional to cosine delta phi. However, if it's smaller than 1, we get this additional sine delta phi function. Now that we kind of have the expectation and the variance of the random variable lambda t plus 1, we can always write down, or we can write down an analogous process, an analogous Gaussian process, which yields the same trajectories of our impact parameter if we just use this procedure to update it. So in each step, we compute the next value of the impact parameter lambda t plus 1 as the current one plus some drift term, which depends on the expectation, and some variance term. diffusion term, sorry. The diffusion term is, of course, coupled to the variance of our random variable. And then in order to bring some random element in it, it is weighted by some random numbers that are sampled from a normal distribution. So as I already said, we will get, because this expectation looks so different, we will get a very different behavior in these two regions. And now let's first look at the region where lambda is bigger than 1. So this was the excursion region in the trajectory. We can then use the expectation and the sine squared, which we computed of our lambda t+1's variable, and consider it for small delta phi. So we basically do a Taylor expansion. This yields then this equation. And some of you may have already noticed that this looks very, this has a well-known form. I mean, it looks very similar to the discrete time Langevin equation. So this Langevin equation simulates basically the time evolution of the probability distribution of our lambda variable. And there the new lambda t+1 values as well computed based on the old ones. And then you have these Kramers-Moyal expansion coefficients. So the first one corresponds to the drift term, the second one to the diffusion term. And you have the same Gaussian random numbers back here. Why is this interesting? Because this comparison with the Langevin equation allows us to set a time scale. Because if we compare these two equations here, you can see that I only need to set tau equal to delta phi squared to have a similar form. And from this time scale, we can conclude that a number of time steps during this excursion scales as some constant over delta phi squared. And of course, you can also conclude that the dynamics of the impact parameter on this excursion follows the Langevin equation. So it will have this diffuse invariant walk. What's also interesting, I mean, we now know at least the time scale of an excursion. We can also look at how the direction changes in total during this excursion, and then we get this additional factor of delta phi. So the direction change during an excursion scales as constant over delta phi. So now we basically understand why this impact parameter does this weird random diffusive walk at lambda bigger than 1. We now have to understand what happens with the dipole angle during this walk. But this is very simple to understand, because if we look at lambda bigger than 1, then we know, assume that we are at some direction phi t, then we know that our blue atom x2 is somewhere in this cap divided by this line, because only in this cap the absolute value of lambda is bigger than 1. We know then we sample a new position somewhere in this cap, and afterwards rotate our direction. So we kind of rotate around this cap, around this inner circle. But as long as we're on the excursion, we know that the position of the blue atom has to stay in this cap. So we know that it kind of follows this rotation of the cap. So if we do a lot of steps, this position xt just follows the rotation of our direction in the same steps of delta phi. So we can conclude that our dipole angle during an excursion also scales as constant over delta phi. And from this, we can say that if we now consider different values of small delta phi that we now assume to be bigger than 0, that they become similar if we plot the change of the dipole angle versus the change of the direction, but we scale both axes by this delta phi. So the plots down here on the left, I show you a plot for where we chose delta phi to be 1 degree, and on the right it's 0.1 degree. And I scaled both axes by this delta phi. And you can see that in both plots, the excursion looks very similar regarding the length, for example. And also, we now understand that in these plots, the slope of the positive direction of a dipole angle is just 1. So we now understood the excursion regime. We're left now with the zigzag regime, so where the absolute value of lambda is smaller than 1. So we go back to our Gaussian process. We again Taylor expand our expectation and variance of our lambda t+1 random variable for small delta phi. And here something interesting happens, because this drift term here is proportional to delta phi. However, the variance was proportional to delta phi squared. This is different to the excursion regime. So in this regime, the Gaussian process becomes deterministic because we can neglect the variance term, basically. And then we have just this deterministic equation of the change of lambda during a single time step. Here, the upper sign corresponds to the S plus regime. So if we go to the phi 0 reference frame, which was the part to the right of the ring, and the lower sign to the left of the ring. And if you now consider the phi 0 reference frame and you assume you're on S plus, you see that lambda always has a negative change because we have the minus sign. So you can view this as we start at lambda equal to 1, and then we always decrease our lambda until it hits the -1 boundary. Of course, then the regime ends. Similarly, in the S minus, the direction is then the other way. So we start at -1, and we always increase our impact parameter until we hit the boundary at +1. This equation here, delta lambda is proportional to delta phi, formulates a non-linear differential equation, and this you can solve. And then you can plot this solution of the differential equation together with the trajectory of the zigzag. And this is what I've done in the plot here. So you can see here, because I plot the absolute value, this single line of this group, a single zigzag, so to say, corresponds to one move, for example, in S plus from lambda equal to 1 to lambda equal to -1. So we can basically write down the trajectory of the zigzag. We also need to understand why the dipole angle is doing these weird steps during this trajectory, but this can also be understood. I mean, now consider explicitly the case I already tried to explain. So here on the right, we have the S plus segment, and we now are again in the phi 0 reference frame where the direction along which we randomly choose a new position is always parallel to the x-axis. And here, for this description, it makes sense to always stay in this reference frame. So what we do on each time step, so to say, we rotate our systems by minus delta phi. So we always have our new move parallel to the x-axis. So the beginning of a zigzag at position A directly corresponds to the position being at the boundary at lambda equal 1 and the S plus. I mean, we could have also considered it here, but I will consider the case here. As I said, I mean, our equation says now that lambda strictly decreases in every time step. So the atom moves down from this position, and at some point it will cross the lambda equals 0 line. At lambda equals 0, something interesting happened, because now I move a position along the x-axis, so to say, but it does not matter which position I choose, the dipole angle always stays the same. So this is why at this position P here, the fluctuations, you can see it in the middle of the plateau, just vanishes. And why do we have a plateau in the first place? Because you can easily see that this position roughly follow the rotation of our system, so to say. So the dipole angle always stays approximately the same. And now the simulation doesn't end here, but the atom goes further down. So it goes down to the end of the boundary. It again follows the rotation of the system, so the dipole angle stays constant. If you now want to have another zigzag, what needs to happen is that this atom now jumps into the other segment, because it cannot go up here again. It has to go up in this segment. So it jumps from position C to position D in 1 or 2 time steps. And this sudden jump of our atom induces the sudden jump in the dipole angle. And then, as soon as this atom changed the segments from S plus to S minus, everything will repeat. We will have another zigzag in our impact parameter trajectory, but now the atom moves up, but it again follows the rotation of the system, so we get another plateau. We can use the solution of our nonlinear differential equation, which is written here, to compute the change of the direction during a zigzag. I've written down the solution here. It looks more or less complicated. The important point is that the change of the rotor direction during such a zigzag only depends on eta, so the ratio of the big R and the small r, so how thin we make our ring basically, but it does not depend on delta phi anymore. From this, we can conclude that the length of the zigzags is constant if we plot the change of the dipole angle versus the change of the direction itself. For the excursion, we had to scale the change of the direction by another factor of delta phi. This is again evidenced by these two plots. On the left, I show you 1 degree again. On the right, I show you 0.1 degree again, and we use the same eta value. And you can see that in both trajectories, the zigzags have the same length. So now we understood the excursions by themselves.
And if I can remark that, so this, what you're looking at is a Markov chain. What you're looking at is a Markov chain. I mean, it looks, look at this picture. Isn't it beautiful? I mean, on the right, isn't it beautiful? It's a Markov chain, right? But it's completely deterministic.
It's very impressive. Yeah, right. This is, we were all really amazed by this fact that we get this completely deterministic and non-random behavior out of such a random process, so to say. And this was not known before, because I said initially this particle and spin indices sweeps always keep this diffusive behavior, but the sweeps of directions do not. So what did I want to say? Okay, so now we understood the excursions by themselves, and we understood the zigzags by themselves, but of course we haven't thought about the interplay of the excursions and the zigzags up to now. So this we will do now. I already explained to you that the number of time steps during an excursion scales as some constant over delta phi squared. However, the number of a time step during a zigzag is shorter by a factor of delta phi, because so it's only a constant over delta phi. At the same time, we know that positive and negative rotations that correspond to excursion and zigzags respectively have to balance. So how do we know this? We know that the expectation of the change of the rotoid dipole angle during nt time steps always has to be 0. This is easy to see because the change of a dipole angle during nt time steps is equal to the sum of changes during all individual time steps. So this is what I've done here, from going from here to here. Then we use that the expectation of a sum of possibly dependent random variables is equal to the sum of expectations. So this is in the second equality here. And then we know that in our scheme that every move of a single time step is reversible. I mean, because we always sample from a flat distribution, so the move from xt to xt plus 1 is reversible. So we know that the change of dipole angle, or at least the expectation, has to vanish. So each of these single terms vanishes, and then we get the overall 0. So I want to emphasize again, we always have to balance positive and negative rotations, and we have to balance excursions and zigzags. Because, however, the zigzags are shorter, this means that the trajectory shows many more zigzags than excursions already. I will say something about this in a minute, but let's first take a look at these distributions of the change of the dipole angle, because they are also very interesting. Because I said the expectation vanishes. This does not mean, however, that the distribution is symmetric. This is especially true because we have highly non-diffusive trajectories of the dipole angle, where we exchange the positive rotations and the negative rotations. So we now first, in this plot, consider only a single time step. The single time step is very easy to even compute analytically, because you just have to integrate over all possible lambda values, and then you can change for each lambda value, you can compute the distribution of the dipole angle change. We can also simulate this curve by just starting a lot of our simulations with exactly one time step that start from all possible initial configurations. You can see this distribution is reversible because, as I said, a single move is always reversible, and then we have to get this symmetric distribution. And you can see that this is also a hint that our algorithm is correct, because the two curves agree perfectly. Of course, we always checked like probability distributions of some variables like rho and lambda to be really sure. However, now consider what happens if we increase the number of time steps to 1 to some higher value, to some moderate value. So we now consider some number of time steps that is smaller than constant over delta phi squared, so not too high, so that This means that some of the trajectories that are started from some initial configuration are still on an excursion. This you can see here on these two bumps. So this blue curve shows 100 time step, and we get exactly a bump at 100 delta phi. And similar for 200 time step, we get exactly a bump at 200 delta phi. And here we can see two other bumps to the left of the mean. I mean, it's this distribution is highly asymmetric. However, the mean is always still 0. So we always can confirm this equation. And now we can also finally consider the case where we choose a very large number of time steps, so that excursions and zigzags can interchange and balance each other. And in this limit, of course, the probability distribution approaches a Gaussian, a symmetric Gaussian. You can see this in this plot here. So this black dotted line shows the normal distribution. And then you can see that if I increase the number of time steps from the blue curve, which still looks a bit asymmetric, to the red curve finally, then you see we approach this Gaussian. So as expected, the mean is always 0, and from this we concluded that the trajectory shows many more zigzags than excursions. We can also try to understand this a bit microscopically in our ring system. Consider again the phi 0 reference frame. So we always choose a new position along the line that is parallel to the x-axis, and assume now that we are at some lambda value that corresponds bigger than 1, that corresponds to this middle line here. We now choose a new position of our atom on this line, and if I choose a new position on this red segment here, then the subsequent rotation of my direction yields impact parameter whose absolute value is smaller than 1. So, and then we go on into a zigzag. If we choose a position in this green segment here, the next value of the impact parameter will be bigger than 1. So we stay on the excursion. If you think about this, and I already depicted this in this plot, I can just increase or move up this line until the full line is green. So this would mean that if I have some lambda value that is above this lambda cut plus value, that I definitely stay on my excursion. It doesn't matter what happens and where I sample my position, I will always stay on this excursion. However, now imagine I explained to you earlier how these zigzags come to play. So, and I said that for one of the zigzags, one possibility is that my atom started down here and moves up in this S- segment until it hits the lambda equal 1 boundary. Now you can see that in order to safely go from a zigzag onto an excursion, it has to overshoot this boundary to over this lambda cut plus value to safe go on an excursion. If it does not do this, there's always a high probability that it goes lands on this red line here, and then it goes into another zigzag. So this is just a small microscopic explanation for why we have many more zigzags than excursions. With this, I basically conclude the explanation of the very interesting, highly non-diffusive trajectories of the dipole angle in our sequential Monte Carlo scheme. And we think this is very interesting by itself. However, to let it be useful, so to say, we also have to study the convergence to equilibrium, of course. So this is what we've done next. There we had a problem that the trajectory where we have the persistent negative and the positive rotations of our dipole angle cannot really be analyzed in terms of autocorrelation times. So what do we mean with this? The autocorrelation terms did not look very exponential anymore. So in this case, we went back to the theory of Markov chains, and we instead consider the so-called mixing times. We define the mixing time as a function of an initial configuration x0 and a bound epsilon. And here the initial configuration depends on an initial dipole length ρ0 and an initial dipole angle θ0. In principle, you would also need to choose an initial direction. However, we can always set phi 0 to 0 because we have this rotational invariance, and only the difference between the initial dipole angle and the initial rotation matters. The mixing time then gives the minimum time where the total variation distance between this distribution pt theta, I call it here, and the distribution pi theta drops below the epsilon value for the first time. What are these pt theta and the theta, p theta distributions? So this pt theta distribution is the probability distribution of my dipole angle after I've done t time steps in my sequential Monte Carlo schemes that all start from the same initial configuration x0. And we want to compute the total variation distance to the desired expected uniform probability distribution of my dipole angle. Here in the second equality, I basically gave you how you can compute this total variation distance. So what you need is basically a very simple integral over the absolute values between the two probability distributions. So we can use our definition of the mixing time that depends on the initial configuration x0 and the bound epsilon to really define the mixing times. So we first have to then consider the worst initial configuration or the most unfavorable initial configuration, which has the maximum mixing time. And then we choose as the bound epsilon 1/4. This 1/4 is not by accident, because then for any epsilon that is smaller than 1/4, one can show in a very general way that the mixing process has this exponential bound. This statement is true for reversible and non-reversible Markov chains, so this is why we can generally use it. Numerically, we can compute this pt theta distribution just by starting a lot of simulations. I think we chose 100,000 simulations that all start from the same initial configuration, and then we get the probability distribution of theta, and then we can compute the total variation distance to the flat distribution. However, in this definition, as you can see, we are still left with the exercise to always determine the most unfavorable initial configuration x0. Luckily, we have a very deep understanding of our ring system because it's not that complex, and we can identify the most unfavorable initial configurations more or less easily, at least for small data phi. So now, for the case when eta becomes small, the most unfavorable initial configuration is the one that yields trajectories that always start with a zigzag. And we can enforce this by choosing, for example, lambda 0 to be 1 and x0 to be in the right segment.
So if I could make
this heat map basically shows the mixing. Yeah.
If I could just make a remark, and Hartmut Monien will certainly agree with us that in mathematics people do it differently from everybody in mathematics computes mixing times, but it has not percolated into the physics literature. But this is the way to do, and all our knowledge comes from this little book that I'm showing you here, right? And it has the mixing times and Markov-chain and mixing times. It's a famous book, and we just follow exactly what everybody in but numerically what everybody in mathematics would do to analyze this kind of thing. Right. Okay.
Yes, I mean, the problem about mixing times is, of course, that are numerically very complex to handle because, as I explained, you have to start, like, what is this, 100,000 simulations for some number of time steps that all start from the same configuration. We can only do this here because we have the numerically simple or easy to simulate system. However, as soon as your system becomes more complex, finding this worst initial configuration is really a complex exercise. But we were lucky that we could do this here, and this will yield very interesting results, in my opinion, at least. So I stopped at the heat map. So this heat map shows basically the time where the total variation distance decayed to 1/4, depending on the initial configuration x0. And you can see here, I draw the red circles, the maximum region or the maximum mixing times exactly at the point where we enforce an initial zigzag. And then I just chose, for example, this point here directly at the left, because it was the most easy to determine. To understand what's going on there, I created a plot for you which basically shows this distribution pt theta, so the distribution after applying nt time steps, probability distribution after doing nt time steps of our sequential scheme versus theta. And I explained to you earlier that in a single zigzag, so all trajectories start with a zigzag, and that the length of the zigzags depends on eta, and we can then, of course, compute the number of time steps during such a zigzags, and this is for this value of eta approximately 146. If you now look at the curves, you can see that for 50 time steps, because all of the trajectories start with the same trajectory more or less, I mean they all start with a zigzag, that you get a very strongly peaked distribution. The same is true for nt equal 100, which is still way below for 146, so we still have this very large peak. As soon as we approach, however, this magic boundary of 146, so the green curve shows 140 time steps, I mean it's still strongly peaked and more or less symmetric at least. However, it kind of then weakens out, because for 160 time steps, some of the trajectories that all started from the same initial configuration continue with another zigzag, and some do a long excursion. And then you get this highly asymmetric distribution. So here we have a strong peak here, and then we have a very long tail here.
Excuse me.
And then...
sorry. This is the first time to see this figure. Does it lay out the expectation of delta theta must be 0 always? Because I see when delta t equals to...
I mean, this is not... this is not the plot of the change of the dipole angle. This is really the distribution of the dipole angle itself.
Sorry, I see the red curve, the change of the theta seems to be non-zero. Yeah, here.
I'm not sure if this is true, but it should be not. I mean, I cannot compute. I mean, I can try to compute the mean or the change of the dipole angle, but I mean, it should be not. I'm pretty sure that. I mean, yeah, you're right that it's kind of. Oops, sorry.
Okay, so.
Let me think for it. Yeah, but I think the reason is really that you're not. I mean, I cannot answer this question right now, but I will think about it for a minute later. Okay. Let me continue first. I mean, now we understood the case for what happened for small eta. I mean, they're bad to enforce an initial zigzag. If we, however, consider, I mean, this function of the change of the dipole angle during a zigzag, if we increase eta, this change gets smaller. So for the larger values of eta, another phenomenon comes into play and gets important, and there it's bad to start with a very long excursion. I mean, and the longest excursion we can start if we choose lambda 0 to be exactly eta. So this is in the phi 0 reference frame. This is where we start at the most top of our ring system. So this is again evidenced by these heat maps. So if you look now at this larger value of eta, but for the same value of delta phi, you can see that the largest mixing time is exactly at these 2 points. And we can again look at the distribution. We can again look at the distribution after nt time steps by starting from the same configuration. Liang, I have the answer, by the way. I mean the saying that the expectation of the change of the dipole angle is only 0 if you average over all initial configurations. However, we don't do that here. I mean, we start always from the same configuration. So we don't have, I mean, now the change can actually change, and basically has to for the excursion, because we start with an excursion. Then what happens is that the dipole angle will travel around with this delta phi, which you can see here. So the difference to the plots I showed earlier is that here we don't average over all possible initial configurations. I hope that answered the question. So let me come back to this plot. So I again plotted the probability distribution of theta. And what you can see is basically what I tried to explain. I mean, if I start on a very long excursion and I choose a very small number of time steps, then all trajectories are still on this excursion where we have a change of delta phi per time steps. So we can see the blue and orange curve here have a very strongly peaked distribution around this expected value pi half, because we started at pi half and then we just add up nt times delta phi. And I computed for you how many zigzags are in this trajectory, and these are 2 time step values where there aren't any zigzags or negligible many. If you now increase the number of time steps to a larger number, so 1,000 in this case, I measured that there are 25% on the trajectories currently on zigzags at this time step. And then you can see that we still have this large bump, of course, because 75% are still on excursions. However, you can see this very long tails which come from these trajectories that end up in zigzags instead. And these splitting up in excursions and zigzags then allows to converge against a desired flat distribution of theta. So for small delta phi, we understand very well what the worst initial configuration is. For large delta phi, the random walk of our impact parameter is no longer described by excursion and zigzags, and then the initial configuration does not strongly influence our mixing time. Notable exception to this are values of delta phi where the period in phi t is small, or the period in our direction. So for example, 90 degrees, because there I first go parallel to the x-axis, then parallel to the y-axis, and then again parallel to the x-axis. So here the period would be 2. Here you can see, if you look at the heat maps, that there an interesting stripe pattern appears. So the mixing time is roughly periodic with our initial theta 0. And this might be, for example, if you consider this theta 0 equal to 0, so our atom is at the beginning in the right part of our ring system, then the first move is basically does not change the dipole angle at all. And this is true during the full initial part of the trajectory. So in the initial part, one of the direction can hardly do anything to kind of mix one of the independent directions. However, it's important to notice in these 2 heat maps that the variations of the mixing time, which you can see on this color bar scales here, is not very large. I mean, at least compared to the small delta phi case. However, we understood this as well, and so we could cover this in our determination of mixing time, where we had to take always the maximum mixing time out of these heat maps. So this is what I will do now. I mean, now we know a way on how we can compute the mixing times, and then we can compare mixing times. I mean, and I will now in the following compare mixing times of 3 different procedures to update the direction. So the first one is the sequential sweeping scheme, where we deterministically increase the direction by this delta phi value, and of course we vary delta phi between 0 and pi. We can also, I mean, if you think about it, in our sequential scheme, we construct a set of directions that are accessible in our sequential scheme. So for 90 degrees, only the direction 0 degree and 90 degrees are accessible, because then we have this repetition. So we can likewise consider random discrete MCMC, call it like that, where we sample the next direction randomly from this set, not sequentially. So this would be like doing random particle indices instead of particle indices sweeps. And the last point we compare to, or the last scheme we compare to, is random continuous MCMC, where we sample the new direction uniformly. So let's look at the first plot of the mixing time for these different schemes. For eta equal 1.1, there are nothing in this plot, at least, you cannot see much, because this full plot is dominated by this natural divergence of our sequential scheme as we go delta phi equal to 0. I mean, because then we rotate the direction very small and we repeat our random moves and along this approximately the same direction. And this is, of course, yields a very large mixing time. However, if you now decrease eta, so we make a very thin ring in which the atom can lie, you will see that something very interesting happens. So this is the next value. We still have this natural divergence of the mixing time of our sequential scheme. But if you look closely here, you can see a small bump. It seems to appear at pi half. And these bumps become more apparent in the next value of eta. And also in the smallest value of eta we considered. So now you see, I mean, we considered, I think, up to 0.1 degrees. Now you see that this divergence becomes smaller and smaller, the smaller we have the eta. And of course, you can always decrease it further. And that at certain values of delta phi, that the sequential scheme and the random discrete scheme show these very interesting bumps. And of course, the random continuous choice does not depend on delta phi, so we just depicted this by this dotted line here. There are several interesting points in this plot I would like to mention. The first is that the mixing time of our sequential updating scheme and the random discrete MCMC are very sensitive to the size of this direction set. What do I mean this is? I mean, these are exactly these bumps. The largest bump we get in both sequential and random discrete at pi half, delta pi equal 90 degrees, where the size of the direction set is 2. The next largest bump we get here. This corresponds to 60 degrees, where the set size is 3. The next bump here corresponds to set size 4. This one 5, this one 6, this one 6 as well, I think. So we see as soon as we increase the set size, we decrease these bumps. And this is true, again, or both for sequentially drawing elements from the set D or doing it randomly. The next point I would like to mention is that sequential MCMC is generically faster than random discrete MCMC, of course, except for this natural divergence, delta phi equals 0. Because in this case, I mean, if I choose a very small delta phi, then random discrete MCMC is basically equal to random continuous MCMC because I just can choose a random floating number. For small set sizes, as for example for delta phi equal to 90 degrees, this is very easy to understand because in random discrete MCMC, we can of course have redundant, repeated move in the same direction. This is not true for sequential MCMC. For large direction set sizes, however, I mean, it is kind of reminiscent of the benefits of doing particle and spin industry sweeps. You can already see here, I mean, the black line always denotes the optimal choice of delta phi in our sequential scheme, and you can see that this black line is below the dotted line. And let's have a closer look at this. So here the plot on the left shows for different values of eta the same plot as before. However, now I zoomed into this region where the black line is the minimum mixing time for the given value of eta. The dotted line is the time of random continuous choice of direction. You can see that, I mean, this is always well smaller, and that the optimal choice of delta phi in our sequential schemes seems to approach 0 as we let go eta equal to 1. The orange curve here on the right highlights that we can always obtain a speed up in our sequential scheme versus the random continuous choice of directions. However, the right curve shows something very interesting, which is that, I mean, I explained to you that the largest bump we get at delta phi equal to 90 degrees because there the set size is only 2. And this yields, if we now plot the speed up compared to this sequential scheme, that the speed up as eta goes to 1 gets very large and even seems to diverge. Why is this important? Because in event-chain Monte Carlo within jellyfish, for example, we always chose the sequential scheme of changing direction by 90 degrees. And now we understood that this might lead to the very slow rotation of dipoles. And that choosing a small delta phi, so a small change of the direction, might may speed up the rotation of dipoles by a large factor. Yeah, so this basically concludes the numerical study of our fast sequential Markov chains and the study of mixing times. Of course, the work is not really done on this topic. There's still a lot to understand. For example, you notice that even for large delta phi, as long as this set of the directions does not become too small, that we can then even be faster than the random choice of directions. And another interesting point is that even for this large delta phi, where we cannot do these Taylor expansions at all, we get very intriguing patterns in the trajectories of the impact parameter and the dipole angle. So you can see here, I mean, this looks very irregular. Of course, it's also always possible to consider more dimensions. I mean, right now we only looked at 2 dimensions. The water molecules in the end will be in 3 dimensions. And of course, you can also extend the toy model. So instead of just coupling 2 atoms by these flat index, you can couple 3 atoms, for example. What we are already working on is to consider a collection of these dipoles still in 2 dimensions. And of course, there it will be really important to apply our sequential schemes to Metropolis and to ECMC, and how to see, and we will see there how ECMC gets well speed up by this idea. And finally, I mean, this is the next step, and afterwards we can then, of course, apply sequential MCMC to ECMC and jellyfish for the molecular simulations we wanted to do initially. So yeah, this was, let me conclude with this slide where I repeat again the most important points of my talk. So I presented to you a scheme where we modify the direction of a local move in any local Markov-chain Monte Carlo method deterministically. So we sequentially increase it by delta phi. I showed to you that this idea profoundly changes the trajectory of the random walk, so it's highly non-diffusive anymore. I also showed to you that this idea can yield more efficient algorithms than the versions where we choose the direction randomly. And the last point is that when we apply this idea to ECMC, that we can get a divergent speedup compared to a naive choice where we choose the velocity parallel to the Cartesian axis. Now I thank you for your attention, and I'm open for your questions. Let me switch off the
leave it on
presentation so I can see you again.
Okay, thank you very much. Thank you.
Thank you.
So
wait, I will do it differently. The problem I cannot.
So you're showing shipwreck?
So Liang, I hope I answered your.
Yeah.
Again?
Yeah, yes, you answered the question.
The picture is showing shipwreck?
Yeah.
Say it again.
Again, Hartmut, I didn't. You.
Unmute.
The picture is showing shipwreck?
I think you're free.
The picture showing, you mean this picture now?
Yes.
I mean, this is just the default Mac OS. I don't know what it is, to be honest.
Good. Okay. No, nice talk, really.
Sorry, I just wanted to switch off the presentation.
So the point really, I mean, that everybody understands that, right? I mean, we haven't changed anything. It's exactly the same Markov chain that everybody does, but the only change is that we, instead of going this way, this way, this way, this way, we just go, we just go this way, and it changes completely. This changes completely. So that's what, of course, this is, I mean, we were so it's so completely surprising. And the whole game of lifted Markov chains is exactly that, right? The original lifting so it's also, you take a particle, then you take another particle, then you move in direct. ECMC is you take the same particle and you move it all the time in the same direction. Changes completely the Markov chain, the behavior, and so on. And I think we'll have work for generations of us, right? We'll work for hundreds of years until we until we understand. And the real point is here, it is not the most random choice of moves that moves the fastest from one, because correlation times is getting away from one configuration into a completely unrelated other configuration, right? That's correlation time or mixing time. And what we see here is it's not the most random moves that mixes up the best. So in this case, we have completely non-random moves, but they mix much better than if we had random moves, right? So we'll have hundreds of years to work on this.
I just wanted to show the trajectory again. So we can...
So in this trajectory, so in the limit of delta phi going to 0, this will go to 50,000 degrees, 50,000 degrees right, then 50,000 degrees left, 50 degrees, and so on and so on. But it mixes faster. That's what Philipp showed you, and it mixes faster than if you do random choices.
Yeah, that's surprising.
Some
Yeah.
more questions? Come on, everybody here. So we have the unique. Where are you, Zay?
Stay there.
Zay is here. Zay, I see him. So he always asks questions. So
Good.
all right.
Well, I will have to leave because I need to eat the next talk.
Okay. All right. So
yeah, no, there are 2 colloquia today, so sorry for saying this, but I mean, there's more work to do for me.
See you.
Okay, Philipp. Very good.
Okay.
Okay.
All right. Then, if there's no more question.
Yeah, and thanks for the talk.
Yeah, thank you. And you'll be able to see it on YouTube. I think so. Very soon. Okay. Bye-bye. Thank you. Everybody.
Bye.
Take care.
Continue our joint meeting, right? Let's continue. Okay. Bye-bye.